Okay, so it's my honor and my pleasure to introduce Peter Stone, who is a professor at the University of Texas and at Austin, and also executive director of Sony AI America. And Peter has been one of the leading researchers in AI, robotics, planning, reinforcement learning, multi-agent systems, you name it, for as long as I remember, and probably longer. He's also one of the founders of RoboCup, and maybe if you ask him later why they set the year 2050 as their goal, he will tell you. Um, and so, Peter, stage is all yours.
Great. Thank you very much. Thanks for the introduction and everybody for being here. Yeah, as Eris says, I do work in a lot of different areas. So I have different talks that I can give. The one today is actually going to be I've never talked about this exact combination of work before, but I just decided I would focus in on machine learning for robot locomotion and talk deeply about two lines of work, one on grounded simulation learning and one on adaptive planner parameter learning. But I'm going to start by sort of stepping back and giving an overview of all of the things that I do in my lab as a way sort of introducing my interests to those of you who don't already know me. But first, I'll say I am a faculty at University of Texas at Austin, and we have some very exciting times there. We were just the National Science Foundation in the United States just had a large competition for national hubs of artificial intelligence, and they awarded 6 last year, and we were awarded one of them on the foundations of machine learning. And so we founded a machine learning laboratory. It's led by Adam Clivens. And so this has been very exciting. We've been growing in machine learning a lot. And then I'm the director of Texas Robotics, where we just opened a new facility. It used to be a gymnasium, and they're turning it into basically a playground for robots. We have now 15 core faculty across 4 different departments who publish in the top robotics conferences in ICRA, IROS, and RSS. Many other faculty who are related to robotics. So it's really, it's when I came to UT Austin 20 years ago, I think I was the second roboticist or second or third, and we've just been growing like crazy. And so it's super exciting. So I hope some of you will get a chance to visit us in Austin. But what I'll lead off with today is my main research question. This is a question that I put on almost all my talks. I've been working on this, as Zara said, for a long time, for more than a quarter century, from long before artificial intelligence was cool like it is now. And the question has always been for me: to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so I publish in some of the sub areas of artificial intelligence in the autonomous agents and multi-agent systems community, in planning, as Zara said, in robotics, and in machine learning, especially reinforcement learning. And if I give sort of this one slide overview of all the things I'm interested in, we do in my lab both work from the bottom up, which I describe as being developing new theory and new algorithms for these areas. But also a large component of my research is what I call more top-down application or problem-driven research. And so in one slide, it's a lot easier to talk about these motivating applications that have sort of inspired me over the years. I have been involved in the robot soccer competition now for more than a couple of decades. This is some video of the robots. I hope that didn't look from my computer like that went very smoothly. Were you able to see that video smoothly or no? Maybe.
No, it was fine.
Yeah. Okay. Okay. Good. Good. So there's these robot soccer competitions where actually I think I might not have checked the box to show videos smoothly. Let me try screen share again one more time. If I do optimize for video. Okay, that should look better. So these are what the robots look like in the standard platform league of RoboCup. The point here is that they're fully autonomous. They have to sense their environment. They have to decide what to do. They have to coordinate as a multi-agent system. This is from the finals of one of the competitions where our robots were playing against a team from the University of Bremen. Here's our robot scoring a goal. And the key here is that, it's not just one aspect. It's not just the vision or the motion or the multi-agent systems. It all has to be put together. So robot soccer, I'll talk a little bit more about robot soccer shortly. Another domain that I work on now a lot is what we call general purpose service robots. This project called the Building Wide Intelligence Project is to try to get robots like this one just always part of the social fabric of our building. So if you come to our building when it's not a pandemic, then you would just see one of these robots wandering around. You don't have to ask us for a demo. It's just there trying to interact with people. This particular video is from some joint work with Ray Mooney on grounded language learning, where the robot was learning through interaction with people on how to improve its understanding of free-form natural language. But the robots, we also have them work on activity recognition, multi-robot coordination. Some of them have arms, and so manipulation. And so really trying to focus on this long-term autonomy. And then finally, I have been inspired a lot by, as many people now, by autonomous driving. I did have a car in the 2007 finals of the DARPA Urban Challenge, as pictured here. I won't show that video. You've all seen video of autonomous cars. We actually don't have this car anymore because all the car companies are investing a lot in autonomous cars. But I do still think about what the world will look like when all the cars on the road are autonomous. Will we need traffic signals and stop signs, or can we have intersections that look more like this? What's going on here? This is, again, from more than 15 years ago. We first introduced this concept of having robots call ahead for reservations at an intersection. And what's going on here is the ones that are white have already gotten a reservation in space-time through the intersection. The ones that are yellow don't, so they have to stop. But once they turn white, they have a guaranteed path through the intersection that won't collide with other cars. And this has led to a decade and a half of research on what happens if now there's a mix of human drivers and autonomous drivers, if we have multiple intersections, if we scale up to full cities, just on trying to use machine learning and multi-agent systems to improve traffic flow. So I could give a 1-hour talk on each of these, on research inspired by each of these domains. But the plan for today is to focus on machine learning for robot locomotion. And I will talk a little bit more about RoboCup because that's the motivation, one of the motivations for having robots that can move quickly and in an agile way. But then I'll do sort of a deep dive rather than staying at just the high level and saying a little bit about lots of things. I'll talk about 2 lines of research. One on humanoid locomotion, and I'll talk about a sim to real method that we've introduced called grounded simulation learning. I'll talk briefly about some of the connections that has with off-policy reinforcement learning. And then I'll introduce some very recent work we've been doing that I'm talking about for the first time here on agile locomotion for wheeled robots and a method that we call adaptive planner parameter learning. So diving right in, as Era said in the introduction, RoboCup Soccer, it has a very ambitious goal. The goal is by the year 2050 to have a team of humanoid robots that can beat the World Cup champions, the human World Cup champions, on a real soccer field. And since it was set up, I'll say, we picked the year 2050 because, that's after all of us will have likely retired. So, if we fail, nobody will be able to hold us to ask us what happened. It'll be somebody else's fault. But it's just it's a nice round number. And there's, and who knows, I still actually don't know if this is something that will seem like it, it's completely unachievable or something that we'll be able to get to there. And, because there's a lot of different components that go into it. I'd like to say we're still in the relatively early stages, although to be honest, there's a community of people around the world now that's been working on it for almost 25 years. So, but there has been a lot of progress. As a challenge domain, it's got a lot of virtues. It's pretty easy for people to get started up on. You can have study multi-robot systems. It's very inspiring. There's different leagues, and they're sort of pictured here. They all have in common that the robots are fully autonomous. And just to give you a sense of some of the progress, this is what RoboCup looked like in the very early years, 1997, 1998. At that time, actually, most roboticists didn't have full robots. They only worked on the vision problem or the motion problem. Integration was, sort of to have a room full with 30 robots moving was a big advance back then. They don't look that great. It's sort of painful for me to watch. They're falling over, they're running into walls. Some of the robots actually caught fire. But then if you jump ahead, even less than 10 years from there, you can start to see huge advances. The robots are moving much more quickly individually. They're working as a team. There's passes. That was the beginning of the humanoid league down in the right corner. So there was just a penalty shot competition that year, but now there's full games in that league as well. And I should say these videos are not my own teams. These are people from all around the world working on on this problem. In different, and each of the leagues has different characteristics. The standard platform league, everybody has exactly the same robots. The middle-sized league has, full-size ball, these sorts of things, the humanoid biped robots. One of the leagues that my team has been, we've actually been winning fairly consistently over the last 10 years. We've won 8 of the last 9 years, is this, the simulation league. It'll feature in this talk, so I'll just tell you a little bit about it. It's this league where it's in a physics simulator, sort of like Majoko. It's a SimSpark, it's called, and the robots are modeled, with gravity and everything. So just getting them to walk and kick is a challenge akin to getting a real robot to do this. But then we can also have 11 on 11 robots, and so work on strategy as well. This is my student's favorite highlight, where the robots are unintentionally kicked it through the legs of the other robot and into the goal. But our sort of secret sauce in this has been a hierarchical machine learning method known as layered learning that has developed some very robust skills for walking and kicking, and that have served us very well. And then finally, I said, the goal is to be able to beat people. Every year now, we play the champions of the middle-sized league, the league that uses the real ball. So myself and some of the other trustees of the RoboCup Federation show that even though we're aging amateur soccer players, we can still run circles around the robots, but every year it's getting a little bit harder. So the robots are getting better. We're also getting older, but one way or another, we're getting closer to the robots beating people. And as I am current president of RoboCup, I should also say RoboCup is not just about soccer. It's about there's an education component. There's a RoboCup rescue domain, and I also participate in a domain called RoboCup at Home, which is about general purpose service robots like this one. The robot, this is a Toyota HSR robot, and the robots are given tasks like taking out the trash or putting away groceries on a shelf. One of the tasks is taking groceries from a table and putting them on a shelf, but having to put items that are similar to each other near each other, and the robot has to figure out for itself what the different categories are. There's also human robot interaction components, like going to a restaurant and taking an order in natural language and delivering it as shown here, where a robot has to find a person that waves at it, go over to it, ask it what it would like, and understand if it wants the Pringles, to go and pick them up and bring them to the person. So there's some really fantastic research that's been driven by this over the years. This year, the competition is June 22nd to 28th, and it's going to be online. So anyone who hasn't seen RoboCup is encouraged to come and see some of the soccer events. It's not going to be a normal competition. It'll be sort of challenges in people's own labs and some much more in simulation, but I encourage people to come and see it. Okay, so that's all by way of just talking about this as a domain, and really there is something for everybody there, and we'd love to welcome more people to the community if people would like to enter either the soccer leagues or the RoboCup at Home or the rescue. But one of the if you do that, one of the skills that will always be essential is getting the robots to move in a very agile way. And so I'm going to focus in now on some methods for machine learning to improve robot locomotion, starting with bipeds and humanoids in particular, and a method that we've called grounded simulation learning. This is joint research with 2 former students of mine. Patrick McAlpine is actually now with me at Sony AI, and Josiah Hanna is about to be faculty at University of Wisconsin-Madison. And And the idea here is that, we'd love to be able to just learn how to have the robots walk on the physical robots. And in fact, for the four-legged robots, for the IBOs, that is some work that I did do back in about 15 years ago. We learned with all of the learning on the real robots, and that made sort of quite a splash at the time. But with humanoid robots, that's difficult to do, because if they don't have a stable walk to begin with, they'll fall over a lot. They can break. It requires you to pick them up and manually reset them. And the wear and tear on the robots can make learning non-stationary. So it's very appealing to try to say, well, let's then learn in simulation. And there you can do thousands of trials in parallel, no supervision's needed. Automatic, you can do automatic resets, the robots don't break. And so you can set up a task like this one, where the robot just has to learn over time to walk in a way that allows it to move quickly or to dribble the ball. And like I said, this is one of the methods that has allowed us to excel in the simulation league, is a new, very flexible way of learning hierarchical skills. The problem is, as many of you know, inevitably, if you learn in simulation and try to just deploy it on the real robot, it can execute, because the policy is the same. There's the same joints in the simulator as in the real robot, but it doesn't work. It doesn't work the way you would expect in the real world. It's it takes a couple of steps and just sort of falls over. And why is that? It's because inevitably the simulator is not perfect, and the learning specializes to aspects of the simulator that aren't true in the real world. And so this has led to a very important and area of research that's been going on and spreading recently, called sim to real, where the idea is that you have your real environment here on the right, you have a simulated environment on the left. They take the same form of policy, so you can execute the actions from a policy in either of them. But the environment is somehow slightly different, because the simulator is not perfect. And so you get different transitions. When you put in an action to the environment, you get one state in the real world and a different state in the simulator, and maybe a different reward as well. And so there's a number of ways to try to bridge this gap. Two general classes of methods. One of them is to robustify the simulator, to inject a lot of noise or extra noise into the simulator, to learn a robust policy, and then hope when you apply that in the real world, that the noise you see in the real world is sort of within the scope of the noise that you injected into the simulator. And there's been some success with that. But the noise that goes into the real world is never, or in the simulator, people tend to inject Gaussian noise. The world doesn't have Gaussian noise. It's still not. It doesn't work perfectly. But there have been some really nice demonstrations of this helping sim to real, with some of the citations at the bottom of the slides here. The other general class of methods is to take some data from the real world and to use it to improve the simulator. And that's the method I'm going to introduce today. Is among that class of approaches. The difference, the general premise though of many people in these who are doing sim to real, is that they're trying to make a perfect simulator. That they're either trying to cover the noise perfectly or use this data to perfectly match the simulator to the real environment. And I think that's a lost cause. I don't think we're ever going to have, at least in the near future, for most complex domains with contacts and gravity, a perfect simulator. And so instead, we're introducing an iterative method that sort of embraces the idea that the simulator will never be perfect, but instead just tries to improve it in the local part of the search space where you're currently looking for your policy. And so we introduce a method called grounded simulation learning that starts with a competent policy. So it's not going to learn from scratch. It's going to require that there's a policy that you can execute. You can then gather some real world trajectories from that. You then ground the simulator, that's the important part. I'll talk about that in the coming slides, but that's the part that makes the simulator closer to the real world, not perfect, but closer. Then in that grounded simulator, you can improve the simulation and then take that improved policy and then repeat, get a new real world execution, improve the simulator again in the new part of search space, and then continue along around the loop. So what do I mean by grounding the simulator? It's trying to make the simulator closer to the real world based on the data that you have. You could just learn a new simulator from scratch on each of these iterations. Because what is a simulator? It's a mapping from state and actions to next state. It's a model in model-based reinforcement learning. But oftentimes you have a very complex simulator that you already have, and it's it may be even it could be a black box entirely, or it could just be very complex physics-based parameters that aren't differentiable. You would need way too much data to learn a full model. That's true in this RoboCup simulator case. So instead, what we try to do is learn a wrapper around the simulator, as shown here, that basically transforms the actions that come out of a policy in a very particular way. So how do we do that? We introduce a grounding function called G, which takes every action that comes out of your policy and replaces it with an action that's a more realistic transition. So what do I mean by a more realistic transition? Well, first of all, and we're going to learn this function G from our data. So what do I mean by a more realistic transition? It's one that if we, actually, I'll just say it on this slide, that if we execute the action from our policy and then change it in the simulator to a hat, that the next state that arises from the simulator is the same next state that would have arisen if the original action was fed to the real world. Okay, so the example I sometimes give is, say I have a joint. Hopefully you can see my. Let me see if I turn on my. Yeah, you can see my finger. So I have a joint that's at like 90 degrees, and I send a command to go to 180 degrees. But in the real world, it's a PID controller. It only goes like from 90 degrees to 120 degrees. And then in the simulator, I tell it to go to 180 degrees, and it actually goes to 170 degrees. So that's the gap. I then instead replace the action in the simulator. Every time the policy says move to 180 degrees, I replace that action with, say, go to 130 degrees. And then in the simulator, it actually goes to 120 degrees, which is what happens in the real world when you send that same command. So that's what we're trying to accomplish. So how do we do this? I sort of just gave you the recipe. We learn a forwards dynamics model of the real world that takes in the state and the action and outputs the actual next state that you would see. And we learn an inverse dynamics model of the simulator, which takes in the next state you're going to see and your current state and outputs the action that would give you that same transition. And so that's the general high-level idea of grounded simulation learning, or we sometimes call grounded action transformation as a particular method of grounded simulation learning, where we're doing this action transformation in this function G as a two-part process. The forwards dynamics model of the real world and the inverse model of the simulator. How do we learn those? That's just as is fashionable these days, we use a deep neural network. We gather a bunch of data, real world. So it doesn't take a lot. We can take 15 real world trajectories of a robot walking that with 2,000 time steps. Each of those time steps has a vector of state and action and next state. And then we can get a inverse model in the simulator by running. It's easier to get more trajectories in the simulator. And so then we can train in the real world, input a state and an action, and try to learn a neural network that will accurately predict the next state, take your state and that predicted next state, and try to learn the accurate action that was used to get that transition in the simulator.
Okay. Can I ask a question?
Go ahead.
Or okay,
please do.
So
yes, please do.
How do you deal with kind of maybe things taking different times in the simulator versus in reality? Like there's a PID controller. It takes time to stabilize, right? And it takes longer in the real world, but you're using a fixed time step, I assume.
Yeah, so the simulator takes actions, accepts actions at this at roughly the same rate. Actually, there's a constant time scaling. I don't actually remember the detail of how. I believe the robot takes actions at 100 hertz and to the motors, and the simulator takes actions at something like 30 hertz or something like that. So there is a part of this that I'm glossing over where you have to try to to make the action cycle line up, and just so every 3 actions for the simulator will you do this mapping. But in terms of how long it takes for the PID controller to arrive, and that is actually often the biggest difference between the real world and the on the simulator. The joints go almost instantly to the place you tell them to. In the real world, it's much, there's slip in the gears, and it's, a real physical process. And so that's exactly what we're correcting for in this grounded simulation learning, is that because the PI, the gains or whatever is causing this sort of fast motion in the simulator, we need to sort of artificially tamp it back and find commands that will lead in the simulator to that PID behavior that we see from the real world. So that's exactly, I think, one of the main gaps that we're addressing with this method in an automatic way. That's a good question. Good, and just to give you some, what some of the results look like, we have, the main goal was for us to go from the SimSpark RoboCup simulator to the real world. There is also a gazebo simulator, which uses a different physics engine, which we can also make sure the method generalizes to a different simulator. And by having two different simulators of different fidelities, we can run a whole bunch of experiments, because any experiment in the real world, even if there's just a little bit of real world, takes a lot of time. So we did apply it to all sort of three transfers, from SimSpark to real, from gazebo to real, and SimSpark to gazebo. Those are all in our paper. I'm going to focus here on the results of SimSpark to the now. We started with a fast walk from, actually the fastest stable walk at the time, from some colleagues of ours at the University of New South Wales. The machine learning algorithm that we use in the simulator is called CMAES. It's a stochastic parallel search method, sort of in the class of evolutionary search methods, but more deliberative than genetic algorithms. So sort of a cross between reinforcement learning and evolutionary methods. It's the method that, and it's shown a lot of success, but it doesn't close the reality gap. And so we had to combine it with this grounded simulation learning. And just to give you, to let you see what the results are, this is the walk that was, that arose, or that we started with, the one from University of New South Wales that goes at 19 centimeters per second. It was the fastest walk at the time. We gathered the real world trajectories, grounded the simulator, went once around this loop. And after the first iteration, got a walk that was already the fastest known stable walk on this robot, moving 26.3 centimeters per second. And then regrounded the simulator, got some more data, and then you got this sort of walk. You see it sort of learned to go a little more squat down to the ground. It's now going 28 centimeters per second, which certainly at the time, and I think was the fastest known stable walk on the robot, and I think is still competitive for that. And and we tried a couple more iterations of this. It didn't get significantly faster, but in our papers we've looked at it in some other domains as well. But this was the initial proof of concept, and this sort of formed the basis for Josiah Hanna's PhD thesis, where he introduced grounded simulation learning. It improved the walk speed by over 40% compared to the state-of-the-art walk engine. And then it has led to a bunch of ongoing work, extended to other robotic tasks and platforms. And it asked us, led us to ask questions of when does grounding actions work, when does it not? There's been some follow-on work that I'm going to briefly touch on shortly. But the other thing is that it's, and this is the other core of Josiah's thesis, was sort of connections that he saw between this grounded simulation learning and off-policy evaluation in reinforcement learning, and also in particular safe learning. So I'm going to take a little bit of a sort of mathematical interlude to talk a little bit about, or give a hint of some of those results. But maybe before I do that, I should ask if there's any other questions on what I've said so far.
So let me just ask you, because I'm familiar with the GAT method. I used your method for one of our applications. So what you showed before, the improvement in speed, you grounded the simulation, and then you learned in the simulation again, and then you tested it on the real robot? Okay.
Yes. Yeah, that's right. So each iteration, there's a little bit of data from the real world, and then a lot of learning in simulation up to stability as much as we can. So the idea is that the simulation is cheap or free, relatively, and real world data is expensive.
Yeah, somehow you mentioned grounding, and I missed the issue that you ran the learning in the simulation. I just wanted to make sure.
Yeah, so if you look at this diagram, so this part right here is the policy improvement in simulation. So that's the grounding is the getting the real data, learning that the grounding function, and then right here is take another whole iteration of learning in the simulator. So every time around the cycle has another one of these policy improvement steps.
Very good. Thanks.
Yep.
Can I have a question?
Yes, please.
Seeing that we have that you gave a huge improvement in robot walking, do you know what is the upper limit in terms of speed?
Yeah, that's a good question. So we tried at one point to calculate the upper bound based on the power that the joints, the motors are able to accomplish, and it gave us something like the robots could move at the speed of sound or something like that. Like it's it's really hard to theoretically say how fast could the robot run move. I mean, it depends on the friction with the ground. It depends on so many things. So we weren't able to come up with a meaningful way, other than saying that the power of the motors, support moving a lot faster than this, of saying, what the upper bound would be. If there's ideas on how to do that with a robot like this, I'd be interested, but we haven't been able to get any traction on sort of a theoretical upper bound on such a complex machine, saying, what would be the fastest it could move.
Okay, thank you.
Yep. Good. So let me move on. And so this is, like I said, I have a few slides here that are completely different from robot learning. It's more general reinforcement learning, but it'll only be a few slides. And then if you're here for the robots part, then you can pop back in afterwards. Some of you though may be interested in this as a just a general reinforcement learning concept. There's a lot, just like we want to be able to learn in a simulator that's different from the real world. There's a general concept in reinforcement learning of trying to learn how to act from data from one policy, and then have it tell you something about what performance would be when you used another policy. So you might want to drive to work from your home using many different paths, and then be able to answer how long would it take if I take a path that I've never taken before, but based on the data from all the other all your past experience. And so this is the concept of off policy evaluation. And so generally it's that if you're given a target policy pi and you want to say how good is it, that's V of pi, we define that as the expectation of the returns, the sum of rewards you get over a trajectory, where the trajectories H are drawn from this policy. They're the trajectories that result when you take the actions according to your policy pi. And so we want to, given a target policy and data generated from a different behavior policy, pi b, we want to estimate the value of our behavior policy, or the target policy. And so we'll estimate it as v hat. And how do we measure whether it's a good estimate? It's if the true value, the mean squared error across all of the states of the true value of this target policy is compared to the estimate is small. So we're trying to minimize this mean squared error. And the workhorse way of doing this is a method called importance sampling. Again, many of you may be familiar with this. It reweights the reward totals for each trajectory in the observed data. So the importance sampling estimate for trajectories H that were drawn from your behavior policy pi b involves two terms. One is the total reward that was experienced along those trajectories from H. And then the other is the relative likelihood of the actions in your target policy compared to the actions in your behavior policy. And so if you know those, then you can, for all your trajectories, you can average the weighted the weighted reward totals, weighted by this first term, and that can give you your estimate of the value of executing policy pi, even though you don't have any trajectories drawn from this policy pi. Now, without going into all the details, there have been two sort of popular myths about importance sampling. One is that if you have access to your target policy, that it's the optimal choice of behavior policy to collect data for important sampling. In other words, if you really care about a particular route that you can drive from home to work, that the best thing you can do is just drive that exact route over and over again and use that as your data. It's sort of only a necessary evil that you have data from other policies. And in fact, the main reinforcement learning book, Sutton and Bardo, says this explicitly. But it doesn't take that much to to realize that that actually, if you, especially in a situation where there's rare events that come up very infrequently, that you could engineer a behavior policy that's different from your target policy, that you could use to minimize the variance of your important sampling estimates. And it turns out, in the limit, if you knew the ratios of the different estimates and the values in the end of the different possible actions, you can get a zero variance estimate in just a single trajectory if you pick your behavior policy perfectly. And so in some recent work, we introduced an algorithm that searches for a behavior policy that gives the lowest possible variance important sampling estimates. We call it behavior policy search. And we first published it in ICML in 2017, and it sort of makes very clear that that you want to try, that there's an opportunity to find behavior policies very different from your target policy that can make learning more efficient. The other sort of popularly accepted myth of important sampling is that if you know what the true behavior policy is that generated the data, that should be what you should use to compute the denominator of these importance weights. So for example, if I'm flipping a coin and I know that it's 50% heads, 50% tails, but my data comes up with 6 heads and 4 tails, that even though it's 60% heads and 40% tails, I know that it's really 50-50. So I should pretend the behavior policy has 50% chance of each action. And it turns out that this is not the case as well. That if you replace, even if you know that the coin flip is 50-50, if you replace it with an estimate of the policy that generated the data, so pretend that the coin is 60-40 because that's what I saw in the data, that will also lower the variance of our important sampling estimates. And at least in this, in the reinforcement learning community, that was not generally accepted before this work, when we proved that using an estimated behavior policy has asymptotically lower variance than using the true behavior policy. And this was published first in a couple of papers in ICML over the past couple of years. So that's just like I say, a little bit of an interlude of some very theoretical general results that are inspired by this sim to real problem. I see them as very similar because it's trying to learn from data that's not reflective of what you really care about, which is the real world for the robot or the target policy in reinforcement learning.
So Peter,
please, go ahead.
Do you have maybe kind of a quick intuitive explanation for the second result? Because it doesn't, I mean, it sounds very unintuitive to me.
Yeah, so it's easier for me to give. So I gave the intuition for the first result. The intuition for the second result is the best I can say is that if the trajectories that you get from that coin flip, right, from the 6, it would be indistinguishable. Like if the coin really were 60-40, right, then the data that you got you would expect it to reflect 60-40. And from the important sampling perspective, all that matters about the behavior policy data is the distribution that it really reflects, or that it apparently reflects. So even if my 50-50 coin gave me all heads, then in some sense the data that I'm using to train on is from a coin that gives you all heads, because that's all of the experience that I've seen. And so it correcting down to what it should have been is going to add a sampling error as well as the important sampling error. So this, the sampling error in the behavior policy By using this the estimated policy, we can sort of eliminate one source of error that you get when you're doing importance sampling reweighting. It's yeah, that's sort of the best I can do intuitively. You have to sort of, you can look through we try to explain it precisely and mathematically in the papers, but I don't think I can give a better intuition than that in words in the time we have.
Yeah. Okay. Thanks.
We can dig into it afterwards. It is
Sure.
interesting though. We did not know when we started. In fact, this was Rich Sutton was on Josiah's thesis committee. He asked them at his thesis proposal. Said this is an open question. Do we know which one is better? Is there a way to think about this? And we dug into it, and I think we've been able to show at least for off policy batch off policy case that using the estimate of the behavior policy is definitively better. So, yeah. Okay, so let me pop back up. If people, that wasn't your cup of tea, the reinforcement learning details, now I'll go back to robotics stuff for the rest of the talk. I've never, the second method I want to talk about, I haven't talked about before, so I don't actually know how long it'll take. So I think in the interest of time, I'm going to just very quickly tell you about some extensions to grounded action transformation. We had two recent IROS papers from 2020. One of them is that we call RGAT. It's reinforced grounded action transformation. I'll just tell you the high level idea of that one is that rather than grounding actions one action at a time, as I've mentioned to you that we do in the method I've talked to you so far, we look at the actions as a sequence and treat the action transformer rather than being two components with a forward dynamics model and an inverse dynamics model. We treat it like a function that's trying to minimize the long-term difference between the simulated trajectories and the real world trajectories. And so trying to not just ground the actions on a action by action basis, but looking at how do they ground over time, over sequences. And so in some sense, learning this action transformer becomes a reinforcement learning problem by itself, where we're trying to learn how to change the actions such that you get the simulation trajectories matching the real world trajectories, which we again can gather from the real world. And it sort of places the agent environment boundary in a different place. It treats this action transformer as the agent, and it's going through a reinforcement learning problem where it's trying to it could now accept having a really bad transition in the near term if it leads to good transitions in the future, which wasn't possible in the method I told you about before. And so we show that this can lead to some empirical improvements. I'm not going to go through the details, just in the interest of time. And we also introduced a method called SGAT, or stochastic grounded action transformations, that because we noticed that the method worked fine if on flat ground, but when we put purposely bumpy ground under the robot, there's like little foam under the carpet here, that the learned policy wouldn't work. And that's because the robot is expecting deterministic transitions in this grounded action transformation function. And we found that if we explicitly and even if the real world has stochastic transitions. And so we found that if we explicitly allow the grounded action function, the function G, to model stochastic transitions, that we were able to learn a policy, and I'll just skip to the result, to learn a policy that is robust to stochastic transitions. So the robot's not sensing these bumps. It's just now on the right is the old method, on the left is the new method, where 4 out of the 5 times shown here, it's able to make it all the way from the start to the goal, even though the transitions underneath the robot are bumpy. And so, again, just very, very brief, if you want the details of that, I'm going to point you to the papers on allowing for sequences of grounded actions and also allowing for stochastic transitions. Okay, but what I want to do with the rest of my time is talk about some very recent work on very different on adaptive planner parameter learning for wheeled robots. So again, if you lost me along the way at any point, now's a good time to snap back into attention, because nothing I talk about now depends on what I've said so far. This is, and the idea here is to try to do motion planning with wheeled robots that leverages both classical motion planners and machine learning methods. So it's not an end-to-end learning method. We've noticed that there's a lot of end-to-end learning methods from pixels to torques. They're interesting, but they never are competitive actually with classical motion planning algorithms. People never, and people don't compare them, or they sort of gloss over that. Yes, it's interesting that you can learn from pixel to torques, but they're still not competitive if you really want to deploy a motion planning algorithm on your robot. You should probably be using classical methods. On the other hand, classical methods have their own problems, and so we're trying in this method, we sort of introduce a way to merge these, to meet in the middle, that leverages human demonstration, interventions, and evaluations. It's work led by my postdoc, Shueishu Zhao, who's about to be faculty at George Mason University, and our colleague Garrett Warnell, and also many students listed here have been involved. So the idea of APPL, as we call it, is trying to be able to deploy robots in very different environments. And one inspiration is that non-expert humans can do this effortlessly, right? We can put the robot in like an obstacle course like this one that has sort of a curvy corridor, an obstacle course, some open area, and the person will very naturally slow down the robot in the narrow places, speed up the robot in the wide open places, avoid the obstacles. And the intuition is that, or the problem is that to get each of those behaviors requires different parameters of your classical motion planner. There's parameters like how much sampling do you do of possible paths forward, and how fast should the robot move, and things like that. And these are very complex systems. Typically, the classical planners. The algorithm that we use is one that's part of the ROS navigation stack called DWA. And there's all kinds of tuning that goes into it. And so the motivation for this work is, can we use learning to sort of come up with a flexible set of parameters for this black box, or treating the motion planner as a black box? Can we come up with some parameters that will work robustly, but flexibly? So different parameters in different locations of the space. And we've actually done this from a bunch of different interaction modalities with people. I'm going to talk about just one of those right now in detail, that we call adaptive planner parameter learning from demonstration, or APPL-D. This is the first one that we published last year, where we use behavior cloning to tune any navigation stack. And so the idea is that our classical motion planner can be seen as a function G that takes sensor data in and some parameters, and outputs motor commands. And these parameters are, it's a long list of parameters that are counterintuitive, that you would never expect a non-expert to be able to tune. And worse, you need a different set of them for every different kind of environment that you're in. And so the idea is we're going to use behavior cloning to learn these parameters from a demonstration using supervised learning to try to find the theta star, the best parameters that minimize the difference between the behavior of the black box algorithm and these demonstrations. Very similar, actually, to grounded action transformation in some sense, is that we're trying to match now a demonstration and the behavior of our algorithm. And so the rough procedure is that we'll collect the demonstration, which is encoded as a sequence of sensors, sensor readings X and actions U. And then we'll take those demonstrations and try to tune our algorithm so that they give us a set of parameters that lead to this minimized loss. And as I've hinted, humans will exhibit in these demonstrations typically qualitatively different navigation behavior in qualitatively different environments. For instance, in this course here, there's like a curve, there's an obstacle course, there's a corridor, and there's an open point, or open space. And to match the human's behavior with one set of parameters here is impossible. And so we need to break this down into context. There's not one optimal set of parameters, there's this sort of set of them. And so that gives us to this, and by the way, I should say, robot navigation, there are algorithms that will do robust navigation fairly well. But when you start talking about constrained spaces like this one that are barely bigger than the robot, if you take any out of the box classical planner, it just fails. It's unless you really go in and tune the parameters for that specific situation, it's going to be backing up a lot. It's going to be running into the walls. It's sort of even though you can put a Roomba in somebody's house and it can navigate around, if you start going to these sort of extreme, tightly constrained spaces, the existing algorithms are not particularly robust without a method like this. So the general pipeline is that we'll collect the demonstration. We'll use in the middle, perform an automatic demonstration segmentation. We use a method called CHAMP, which is from a colleague, Scott Neekum, that is sort of a way of taking demonstrations and breaking them automatically into similar contexts where you can where they're giving qualitatively different behaviors. It's a Bayesian method that we just use out of the box for this. And then we try to learn a set of optimal parameters for the given situation, and then learn on top of that a context predictor. So it's one that, given your sensors X, which of these sort of automatically segmented parts of the demonstration are you closest to? And so then at deployment time, that was messed up. But at deployment time, we basically take the sensors, use it to figure out first what context you're in. That outputs your tuned set of parameters for that context, and then you pass that into your motion planner, and out come the actions. And so we were able to do experiments on a clear path jackal, where one of the authors used an Xbox controller to demonstrate the robot moving around. The environment is this one that I already showed. These are actually supposed to be videos playing, but they're not showing. Okay, but you'll I think there's a video later that you'll be able to get to see it working. Is that as it moves through here, you'll see it like in the vanilla, the default parameters, it ends up sort of really struggling through the narrow corridor, and then moving too slowly during the open space. Whereas when with our robot using APPL, it ends up moving appropriately slowly and avoiding all the obstacles in the constraint spaces, and then speeding up in the open space. And I'm sorry those videos didn't run, but then we can get quantitative results as well, and look at what the behavior loss is for APPL, our method. Our APPL, if we don't separate by contexts, if we use the default parameters that come with the motion controller, or if we just use the raw demonstration. The demonstration, of course, perfectly matches the demonstration, so there's no loss. But you'll see that the default parameters work, definitely better in some spaces than other spaces compared to the demonstration. And especially if we look at traversal time, we find that that APPL, where it takes into context, the green bar here has much lower traversal time than either of the other methods, than the default parameters or not considering context. And then we were, in addition to having it work on the jackal, we were able to get it to work right out of the box out on a different robot, where the default parameters that would have the robot sort of take a very curvy path. We were able to tune it manually to take a slightly better path, but the learned behavior in this open space is able to go straight and quickly to the goal. Again, there's we have videos of all of this on our website, which I encourage you to go look at. So
Peter,
go ahead. Yes.
Do the parameters that you learn, or the context that you learn, does it depend on the goal as well, or just kind of on the local sensor?
Local. It's all based on local sensing. Yeah. So this is a local control algorithm. The global path planning can be done with any other method. It's sort of plug and play with if you're using A-star, or you're using something to get you the global path from your current place, and then the local planner is telling you how to move the motors, or what commands we send to the motors to get through our local the local space, and that's what this focuses on.
So this assumes that the robot is kind of pointing in the right direction, more or less, right? And wants to move forward. And
That's right.
and okay, got it.
Yeah, so it's basically taking I think it's planning to the path that's 2 meters in front of it according to the global plan, and always doing that.
Right.
Yeah, that's a good point. I should have mentioned that this is focused on local. Okay, I know I'm running out of time. I'll just say we have if you go to the web page where we introduce this method, we have sort of related methods that to APPL-D that allow for different interaction modalities with people. So in some cases, you don't have if it's too cumbersome to get a full demonstration, we introduce a way where a person can just intervene when the robot does something wrong. So the person can just watch the robot doing its thing, and then if it has trouble, like it runs into the wall or it like looks like it's having trouble getting through a narrow corridor, we call that a type A intervention. The person can sort of back up the robot and say, here's how you should have controlled yourself through that space. Or if the robot is behaving okay, but suboptimally, like going very slowly on this open space, the person can back it up and do a type B intervention that says, it's not, you didn't do anything wrong, but here's better. You can move more quickly. And so, and we say, we experiment with, what happens if we only do one type of intervention or the other type of intervention. And again, show that this actually performs sometimes better than APPL-D because we find that the demonstrations are sometimes suboptimal in the place where the robot's already doing well. Another type of feedback that sometimes people give where they maybe, like I can't control, sometimes there might be a robot that I can't even control myself, like I can't fly a helicopter, but I could give feedback, just good job or bad job. And we call that APPL-E, or just Apple, for evaluative feedback, where a person can just say good job or bad job, and the robot can try to improve performance based on that. And then finally, we introduce a method that doesn't use any human feedback. We call APPL-R, that basically makes the actions of the policy that's learned using reinforcement learning the parameters of the motion controller. And so this is hard to train in the real world. We actually train it in a new benchmark data set that we've introduced called BARN, Benchmark for Autonomous Navigation, that has environments ranging from very open and easy to very cluttered and difficult. There's 300 environments, and the robot learns through experience in these environments to be able to change the parameters of its control algorithm adaptively, potentially even every step along the way, to come up with a policy that allows it to navigate through robustly. I did see in the chat someone asked, where can you see the presentation? I believe that the presentation is being recorded, but if you want to get the details of this, if you just search for Apple and my name, Adaptive Plan and Parameter Learning, or especially Shui-Su Zhao's name, XIAO, Shui-Su has put together a very nice webpage that has videos of each of these different methods and pointers to all of the papers. And so finally, what we're working on now, this is in preparation, is putting these all together and thinking about, like, what would be the cycle of learning for a robot like this one if it were developed in the factory. You might use this reinforcement learning method to learn a general purpose control policy, and then improve it through demonstrations, interventions, and evaluations to get some new data that you could then return back to the factory of new environments and new situations where the robot failed, do reinforcement learning again, and sort of put all of these methods together to adaptively tune the parameters of our planner. So that's basically what I wanted to say. I know I'm out of time. Just as a summary, this is my high-level research question. If I did have more time, I could talk a lot more about some of our other reinforcement learning contributions, or some of our multi-agent systems work on ad hoc teamwork, which I actually started when I was on sabbatical in Israel. But I'm going to pass over that and just end here. So if in case people want to ask questions, and say that, remind you that my top level research question is this one: to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? This particular talk focused on the learning, not so much of the teammates and adversaries. There's other work that does that. But in this talk, I focused in on giving some motivation for RoboCup, introduced for humanoid walking the method of grounded simulation learning, and which is illustrated here, and talked about its connections to off-policy reinforcement learning. And then in the end, sort of, a little bit of a whirlwind. I know I went very quickly through it, but I introduced our method for adaptive planar parameter learning for wheeled robots, as illustrated here. So with that, I thank everybody for your attention, and I'll be more than happy to stick around and ask questions or answer questions.
Thanks, Peter.
I know there were questions throughout the middle, so if there's no more questions, I won't be insulted. That's okay.
Maybe I'll ask one more thing about this Apple thing, the Apple within a thing. Seems like it would be possible to crowdsource.
Yeah, so that's right. So we have looked at that. So it's actually very related to an algorithm that my student Brad Knox introduced called Tamer, which is a general reinforcement learning for learning from evaluative feedback. And yes, we sometimes do gather data like on Mechanical Turk. We're actually doing some research right now with Brad. Actually, we had a paper at the Coral Conference last year that we call learning from implicit human feedback, where rather than a person explicitly saying good job or bad job, we watch their face and based on their reactions, try to say, oh, is this what the person wanted or is it not, right? So you could imagine, like in an autonomous car, if a person looks scared, then you might say, okay, I didn't do the right thing. Or if they look calm and they're talking to their friend, then okay, I'm driving well. And so to gather data for that, we did do some in-lab experiments, but we've also used some Mechanical Turk experiments where we do crowdsourcing to try to get what are the range of expressions you might see. And so yes, very much. Then you might, so the question now is, are you trying to learn a general policy from a group of people, or are you trying to, be a customized robot for your particular, the particular person in their own home? And so that will dictate whether you want to, crowdsource or whether you want to get the feedback from just a single person.
Good point.
Sure, I have another question.
Please.
Did you think about the way by which a robot can understand that it needs the help of a human demonstrator? So understand that it needs help in general, or that it can't achieve a goal, etc. Do you have any thoughts on that?
Yeah. I guess I shouldn't say I have done. I mean, we've thought about that. We do have some robots that don't have arms on them, that have to go through doors. And so they, like I showed you the video at the beginning of our building-wide intelligence robot, if it needs to go through a door, we have had it go and ask people for help. Or if it, doesn't have an arm, it can, it can't press the button on the elevator, so it'll go and ask a person. But those are sort of hand-coded in ways of it saying, I need, like it knows that it can't open doors. It knows it can't push elevator, buttons, and we just tell it that. I think it's an interesting question. I think this is something that other people have looked at more than we have. So I think it's something that would fit in very nicely to this whole, especially the building-wide intelligence project. But that's not something that we have anything specific to say about right now. I mean, we are doing, I think about some of the work that I'm doing with Mirsky and William Mackey in a multi-agent setting where the robot, where an agent is deciding when to communicate and try to, and it's based on some of your work as well on, trying to, in the plan recognition sense, trying to recognize when is the high value time to ask for information. And so so I'd say that that's the work where we're doing, more of this, sort of reasoning about when should you try to gather information from people, or when should you try to just keep acting based on what you're doing, based on expected case plan distinctiveness and that kind of thing, which is, like I say, based very closely on some work that you introduced. But in terms of putting it onto these real robots that I showed here, we haven't done any of that yet.
Thank you. Great talk.